you can see that it's not about CO2. It seems to be a general thing that within a reasonable range of growth rates, if you grow faster, you're actually a crap competitor. All the competitors do better than GFP because Austriococcus hates GFP. So we said, okay, why are they such bad competitors? And we set off to measure stress. And what I'm showing you here is mitochondrial potential. One of the lovely things about Austriococcus is it has a single mitochondria. So you can actually stain the mitochondria with potentiometric dye and use a cell sorter to measure the fluorescence. So you can use rhodamine 123 in the end. So you don't have that confusion between the number of mitochondria taking up dye and the potential of each individual mitochondria. There's one. And the cells above the line, so this is the control in the control environment. This is how much mitochondrial potential they have. So any cell with that much or more mitochondrial potential we decided was pretty normal. Any cells with below that mitochondrial potential we decided were probably not quite normal. And what you can see is that these cells over here are quite stressed. And what these are is these are the high CO2 cells that have failed to reduce their growth rate. So it's kind of an interesting thing. So basically, the faster cells were growing, the more stressed they were. So here are the high CO2 cells that evolved in the fluctuating environment where their growth rate was really, really reduced. It went back to ancestral growth rates. So plastic response was to almost double their growth rate by the end of experiment. They had completely undone that plastic response. Here's their mitochondrial potential in high CO2. They still don't like ambient CO2 so much. These are the high CO2 selected lines that grew without any sort of fluctuation. These are the ones, by the way, so these are the ones with these fast growth rates. And here's the mitochondrial potential at high CO2. And these are the control mitochondrial potentials at high CO2. So that's not conclusive, but it's certainly suggestive. We measured how wimpy there were. So we thought, okay, maybe they just are generally unhappy. Maybe these cells are just barely hanging on. And so we do what anyone would do, we tried to kill them. So what I'm showing you here is a heat shock assay where I'm showing you the growth rate before heat shock in orange and the growth rate after heat shock in blue. These are control lines selected in the constant environment. These are the control lines selected in the fluctuating environment. And what you can see is Austriococcus does not like heat shock, but it survives heat shock. Its growth rate goes down by about 40%. So this is, just for reference, this is the usual growth rate of Austriococcus in a normal CO2 environment. This is the usual growth rate after heat shock in a normal CO2 environment. These are the control lines grown in a high CO2 environment and then heat shocked. So here you can see there's a clear increase in growth in response to CO2, right? So these were ones grown for 400 generations in the control environment, placed in CO2 for a week, in high CO2 for a week, and then heat shocked. And actually you can see that in the short term, high CO2 is protective. So in the short term, this is a great environment. It is in fact so great that you're completely immune to heat shock after 1 week. This is great. So if you take physiology experiments and you say, what is the effect of high CO2 on Austriococcus? You're like, it makes it into super Austriococcus, right? Here are the lines that evolved in the high CO2 stable environment. So you can see their growth rates have reduced relative to this plastic response. This one's gone back to pretty much the control growth rate. And here's how well they survive heat shock, which is pretty much not. And these are generous estimates because we only measured the growth rates of the cultures that actually grew. So we didn't include any zeros in this data. But most of the cultures actually died. So that was a long discussion with reviewers. We finally went with the conservative bars. And this is in the fluctuating environment. So these are ones that managed to reduce their growth rate at high CO2 quite significantly. So here's the growth rate of this high CO2 evolved line at high CO2. This is the high CO2 evolved line at high CO2 with high growth. And what you can see is it survives heat shock almost as well as the control lines now. So reducing your growth rate is correlated with both having more mitochondrial potential or higher mitochondrial potential and also being less wimpy. And I can just sum it up. There we go. Fast-growing cells are wimpy. So what's the take home? This is the plastic response to high CO2. This is just the growth rate, population growth rate. I'm pairing these up for you. These are control cultures, control evolved cultures, exposed to high CO2 for short periods of time. These are controls, these are fluctuating controls. You can see you increase the CO2, their growth rate increases. This should not be a surprise at this point in the talk. However, this is the evolutionary response. So this is the plastic response to high CO2, and here's the evolved growth rate at high CO2. So you can see, at least in the fluctuating environment, the plastic response is completely reversed. So now they're growing in this rich environment at the same rate that they used to grow in the unenriched environment. And our hypothesis was that this plastic response is taking advantage of a temporary nutrient increase, and this is optimizing quantity versus quality of offspring in a high nutrient but very stressful environment. Now, the environment doesn't appear stressful at first, right? Because it makes them into super Austriococcus in the short term. But in the long term, these cells are obviously stressed out. Their mitochondria aren't working that well, and they can't survive even reasonable heat shocks. Okay, this was not like 80 degrees. This was 30 degrees. For strains that were coming from the Mediterranean, 30 degrees is not outside what they experience. So it was really shocking to us that they were almost unable to live through what we considered a pretty standard environmental perturbation. So I talked about growth rate in Austriococcus, but this kind of phenotypic reversion has happened in every single high CO2 experiment that I've done over the past 16 years. And for every experiment, I've written it off as having to do with the organism or the experimental setup. But I feel like if you're really shooting like 100%, that there might be something there. It happens for traits other than growth. I've talked about growth here because it's easy, but it also happens for things like chlorophyll content and cell size and photosynthesis rates. Critically, it means that the phenotypic outcome of these evolution experiments depends when you stop the experiment, whether or not these traits have time to revert or not. Yes, so all of these traits can revert, and I wanted to know if there was a general explanation.